Okay, well, I think we might as well begin. I don't expect anyone else. As I mentioned, Dr. Georgiev will be not here today, but he's resuming his series of lectures next week. Today, I think we agreed during our last meeting that we would spend most of this meeting on discussions of various issues. One issue in particular that has come up is courtesy of Dr. Sobczyk in his continued development of what he refers to as isogeometric algebra and isogeometric calculus. And so for me, that seems like an interesting approach to understand isomathematics in general. Although I think that Dr. Santilli has suggested that it's not necessarily the most general kind of isopathy that one might wish to consider in physics. So maybe there is some limitations in that, but still, for me, it does provide a conceptual tool to help understand, at least in a more intuitive way, what isopathy is all about, so what implications it has, and so forth. Yes, Dr. Santilli?
Yes, allow me to clarify, please. I found the Clifford Arthur extremely interesting and extremely powerful. And it appears from what I have seen, it's now a joint paper with Dr. Sobczyk regarding the representation of nuclear magnetic moment. I found the features of the Clifford algebra that I could not do with other isotopy. So this is quite powerful, quite powerful. I do not know whether the universality is another method. But let me put it this way: without the Dr. Sobczyk Clifford algebra, I would not have been able to achieve that particular realization of bomb-seed and variable. So I think they're very powerful, very interesting indeed.
Okay, well, yeah, I think that the advantage of the Clifford algebra, it does offer geometric interpretations rather than just doing everything in terms of matrix algebra. It actually considers matrix algebra as a coordinate algebra of Clifford algebra. So I think that's the main advantage of Clifford algebra, or geometric algebra, as we like to call it. So,
I think that seems to me to be a really important and essential point, really, because
yeah, I agree that perhaps that the power of the Clifford algebra is precisely the subject what you indicated, namely is a geometrical approach. That's the power. That's geometry may well be the ultimate essence of.
And I think
yeah.
Dr. Santilli?
I'm sorry?
I'm sorry, Dr. Santilli, could you repeat what you were saying? I didn't hear your...
Sorry, it appears that the power of the Clifford algebra may be precisely in their geometric characterization of nature, if you want, because it may well be that the geometry may be the ultimate, at least one way to axiomatize, to represent some aspect of the universe. So it's a plus. The fact that it's a geometrical approach is a plus, in my view.
Well, what's interesting to note that whereas it does give a geometric interpretation, there are various isomorphisms between algebras, so you can really go from one geometric interpretation to another depending upon the requirements of the physics behind it.
But from the point of view of considering matrix algebra representation, it suggests to me that isopathy has mostly to do with representations of algebra. You know, that Clifford algebra and iso-Clifford algebra are isomorphic and really equivalent. It's the representations of those algebras which are modified by the isopathy. So when you say, for example, that geometric algebra is coordinate free, then I'm concerned that we aren't really, how should I say that? That all we're talking about is transformations from one representation to another, but within the same coordinate-free algebra. So we haven't really done anything to the algebra at all. We've only modified its representation in a certain way. And for me, that constitutes a kind of concern, at least, and that I think was very well expressed by Olszewicz in his desire that physics should always be expressed in a coordinate-free language, so that the moment that you resorted to a representation of an algebra, that was a matter of choice only of convenience, and that we make a more convenient representation for certain purposes, but ultimately the physics itself was represented by the algebra, by the abstract algebra.
Yeah, I think that's correct. In fact, so you don't need to, with geometric algebra, you don't need to represent it as a matrix algebra, but for example, doing computations, it's very handy to be able to, especially with software available for matrices is universal. So to be able to use it, go to a coordinate matrix, it allows you to do calculations just simply with matrix algebra. But I think that the most important thing is the decomposition in Clifford algebra into symmetric and anti-symmetric parts. And I think that's where really the physics comes in. For example, orthogonal vectors will anti-commute. So that has a geometric interpretation right away. It can be hyperbolic vectors or Euclidean vectors. And of course, even the definition of whether you have a trivector or a vector, in one algebra, you might want to consider it a trivector, but in another algebra, it's just a vector. Well, that's where the isomorphism between these Clifford algebras, you're really quite free on how you want to interpret it. It could be a vector in one algebra, but a trivector, for example, in Dr. Santilli's applications, becomes a volume element in another. And that's, of course, where this idea of an iso unit becomes important, because that's really, when you talk about iso-Clifford algebra, you're really changing the very notion of a unit. But at the same time, what you're doing is you're preserving the anti-symmetric structure, but it's the symmetric structure that's being changed in a radical way, and that you're changing the unit, the iso unit. And of course, you're using that also to find multiplication.
However, it appears that we're still within the framework of a realization, because to my best knowledge, at least the dream, the assumption is that at the abstract level, abstract coordinate free or realization free, the isotopy should not appear, should not exist. They do not, by assumption. They have to be, for instance, the Lorentz symmetry. If we do an isotopy, it is Lorentz. Indeed, we don't call it iso-Lorentz, we call it Lorentz isosymmetry, because the axiom are all Lorentz, identical. There is no change. At the abstract level, the computation rules are, there is a clear isomorphism. So it's a question of, so in physics, what appears to be very important is realizations. To realize the algebra with the conventional commutator, then I know no way to represent strong interactions. If we realize exactly the same algebra, for instance, SU2 spin algebra, if we realize it with the isocommutator, then I see the degree of freedom, which is the isotopic element, allows me, at least allows me, to initiate, a primordial, let's call it, without any reservation possible, but at least it's something, because it is now 1 century which we are talking about strong interaction. There's no way. But then we end up with the consequences is reassuring, because nuclei, this is a point we raised the other day in other meeting, the nuclei are composed by proton and neutrons, as we all know. But protons, as we all know, they're positively charged. This means they repel each other. Protons will repel each other. This is not said in graduate schools. And then one of the objectives is what is the stability of a nucleus? We are alive because our nuclei are stable. So this means that there is a force strong enough to overcome the Coulomb repulsion. By keeping in mind that at 1 Fermi distance, the Coulomb repulsion between nuclei is astronomical, enormously big. We're talking about hundreds of Newton. Newton is microscopic. So the implications, the importance of realization but with isotopic algebra, we have a chance of overcoming this repulsive Coulomb force, and we have a chance. But with Lie algebra, I bet my life and my honor, there is 0 chance. Indeed, in 1 century.
But wouldn't you agree that Lie algebra is also coordinate free?
It can be represented, yes, in a different way, certainly. Absolutely.
Yeah.
In fact, the Lie algebras that we're dealing with are really the same as the Lie algebras in the standard treatment, because the anti-symmetric product is what's conserved, it seems to me. So we're dealing with exactly the same Lie algebras, but the geometric interpretations become different, I guess you can say.
The Lie algebra, Lie isotopic algebra are isomorphic by assumption, and if they are not, the isotope is not correct.
Mhm.
At the abstract level, you lose the distinction. You lose the distinction between. This was my point, that in physics we need the concrete realization. In mathematics, no. I love the beauty of mathematics, in which you reduce everything to primitive axioms. So mathematical viewpoint is different.
But if we were to be able, for example, to use Clifford algebra at the abstract level to describe forces or interactions, then I like if the description was abstract, then I don't really quite understand the need for the isopody, other than as a convenience tool for calculation. If we accept that the physics is in the algebra, and not the physics does not depend on how we choose to represent the algebra, then to the extent that we can perform all of the calculations abstractly at the abstract level, then we have achieved that, the goal of, say, explaining nuclear forces as arising out of the fact that at a fundamental level, physics is due to the abstract structure of Clifford algebra. And I don't see that we need to say much more than that, other than that it's just sometimes convenient to use one choice of basis and sometimes convenient to choose another choice of basis.
Well, the most extreme thing different between those isoalgebras for me is that the choice that you're not using a unit becomes a multivector, or it can be a mixture of all kinds of different.
But that also harkens back to, at least in my mind, to what Bolshevich tried fairly strongly to achieve in his work on Clifford algebra, was to sort of remove that distinction between vectors and bivectors and trivectors, so that this notion of the what's the correct term, the order, the term escapes me at the moment, but the grading, right? So so that grading is not an essential characteristic of Clifford algebra in some way, right? That the algebra
well, that's
exists
interesting
independent
what
of the
you're saying
grading.
about that. Because in a way, this Clifford algebra structure really, well, has allowed me, for example, to identify a matrix as a product of actually nilpotents. All the elements of a matrix can be written as a product of nilpotents, and that's, of course, an element which has square 0. So for me, the only way I can see that is in terms of the Clifford algebra structure, that every matrix can be represented, all the elements of a matrix algebra can be represented as products of nilpotents. So for instance, a nilpotent, that is an element which has square 0, seems to be the most fundamental element in physics or anything else too. Well, the idea of a linear structure somehow is intimately tied up with the idea of a nilpotent.
Well,
Square 0.
power of the Clifford algebra, I believe, because that's nilpotency is very predominant in Clifford algebra, as far as I can see, and it is such an original conception. You know, very structurally beyond conventional Lie algebra. It is a question of it is perhaps the reason of the plus offered by the Clifford algebra.
So I think Spicek was very happy with abstract structure, while a nilpotent, of course, has a very simple algebraic structure, namely its square is equal to 0. But that's just the beginning of it, of course, because you have
Then of course they're
nilpotents, then it becomes important.
also, of course, idempotents are algebraic representation of projectors, right? So
That's right. And in fact, an idempotent, usually on the diagonal of a matrix, can be expressed as a product of 2 nilpotents. That's an important point. What I call compatible nilpotents.
but algebraically, they do interact with the notion of unit as well, of course.
Oh, that's right. That's right. So, well, yeah, this idea for me is trying to understand the role of a iso unit. Well, of course, the product then is defined in terms of the reciprocal of a unit. The inverse of the unit becomes the element that Dr. Santilli uses with T, capital T.
But it seems to me, though, that just represents a change of coordinates, right? And that
the change of what?
Change of coordinate.
Oh,
a change of basis.
Yeah. Yes.
But a change of basis in a general sense of Clifford algebra.
But because I have here a different interpretation, because maybe we can understand iso numbers like one ideal in the ring. And then
an ideal.
Ideal, yes, ideal in the ring. And then this is a universal expression of this. The only thing here is that we are working only with ideals, no? Ideals. And the other thing that I don't understand at all, but is the mapping in the operations. Because in iso mathematics, we have two things. One is work with ideals, and the second is work with mappings of all the operators. All the operators. In one book that you recommend to us, Professor Ruggiero, this that was written in Spanish.
Come for me. Yes.
Okay. In this book, this start with one excellent review of all structural mathematic structures.
Mhm.
And they use not the conventional symbols for the operators, for example, plus, dot, etc. In each mathematical structure, they use one different symbol. And I think that this difference is very important, because after when they arrive to isomathematics, then the idea of mapping is fundamental here. Then if we can combine the idea of ideals and the idea of mapping, then I think that we can recover the isomathematics.
Yes, yes, indeed, it's the map. It's the form of the map is debatable, but I agree fully, Dr. Cruz, yes, indeed.
Okay,
When you refer to mapping, are you talking about like a morphism, like from algebra morphism?
Yes, algebra morphisms. Yes, because we convert for example, plus in plus by t, 1/t, no? For example.
Mhm.
And all the operators have the same treatment, no? Treatment, the same. And then in the last exposition by Georgiev, we can get that he systematically are transforming all the operation in including the unit in the operation systematically. And I think that we can interpret this ISO mathematics in this way.
Mhm. But do you think that this notion of mapping is not represented sufficiently by the notion of a change of coordinate, right? There's a change of basis.
No, because this is I am interpreting this like a new kind of morphisms, a new kind of morphisms in the algebra.
Mhm.
In this way, maybe we are seeing a new kind of structure here.
I think maybe this is actually quite. Oh, sorry, Dr. Santilli, you wanted to say?
Just before we pass to another, allow me to clarify one point again, the physical part. While the change of coordinates are perfectly okay mathematically, but physically they are a total disaster, an anathema, because everything has to occur in the actual coordinate of the experimental, or because otherwise the mathematics becomes too vast. And indeed, there is this notion of direct universality, namely that a law has to be universal, fine, but has to be direct, means directly in the frame of the experimental. So this is why we do not represent the Lorentz ISO transformation via transformation of coordinates, even though theoretically it's possible. We don't, because otherwise they will lose physical meaning. Instead, the mapping going from Lorentz to the iso-Lorentz should occur in exactly the same coordinates to be applicable.
Well, but this was emphasized by Ushevich, I think. I mean, he was saying, for example, that what we mean by space, physical space, is dependent on the observer. that he wanted to say in several papers that there is no space in physics, at least not in any absolute sense. That the only sort of absolute thing might be something like space-time, or at least the space of events. And then how we obtain our description for a given observer, right, is in fact related to this notion of mapping, that we're mapping from the absolute algebra to a kind of relative algebra. Both are represented in a fully abstract coordinate-free way. So this, and I understand, of course, what you mean, Dr. Santilli, when you say that in order to relate physics to the measurements that an observer makes, we have to be able to map our physics into the coordinate frame, or into the space of a particular observer. Well, Shevich wanted to insist that relativity was a very general concept, had nothing to do with velocity of light and so forth. It had to do with how we obtain those types of mappings from one observer to another observer, but retaining the same physics in some absolute way.
Okay, well, I'd like to discuss a little bit the notation that we use. That was my problem. That I can, if you allow me to share my screen.
Yeah. Yes, I think I was going to mention too that I think the comment you make in the page 5 of your draft paper, Dr. Sobczyk, is quite, all of our discussion so far leads into that quite well, because it is the issue of how do we map an operator like differential. How do we do that successfully? Mapping a differential in one algebra
Exactly.
to a differential in another. So
Yeah, that's my basic problem with Dr. Gia's, where he introduces so many different, he introduces a different ISO unit for every dimension. And that to me it becomes pretty unwieldy actually. So, but perhaps Professor Santilli can say more why that's necessary. But so if I can share my screen, we can quickly go through.
yes,
those
please
ideas.
continue.
Okay, let's see here.
If I may say, while we wait for the screen, is that Dr. Georgiev approach of introducing an isotopic element per each coordinate is more connected to the idea of representing isotopy by coordinate transformation. In other words, a coordinate divided by its own isotopic element can be considered a coordinate transformation in that sense. That's one of the reasons we don't do it in physics. We use the isotopic element. If you are in 3-dimensional, we use the iso unit as a 3-dimensional matrix. Eventually, we'll end up with a generalization of the invariant identical to that by Dr. George, but then the results are similar, if not identical.
Yeah, I'm trying to find out how to.
At the bottom of your screen, in about the middle of the screen, you should see a button that says share screen.
Yeah, I found that button, but then it takes me to a portion of screen. I'd just like to share my desktop, and I don't see how to do
yes,
that.
there it will. When you click on share screen, you should see sort of individual possible choices, like as a series of boxes.
Maybe that's
Yeah,
it.
yeah, there you go. That looks perfect.
Okay, see if I can, but except it's not, see if I can increase.
Seems a little bit too large, or or at least the scale is a bit
Okay.
off scale.
I do have still a problem here.
I see the title and in the first section header.
Yeah, I
But
just see
it
that
looks
too,
so-
but
It
how
just
do
looks a
I,
little off to the side.
yeah, I can see the problem. I'm trying to, maybe I should.
Are you using Acrobat or something like that to?
No, I'm just trying to but I seem to be a little bit hung up here.
Mhm.
Yeah,
You
my
have another
computer's-
option is that instead of sharing just an individual window, you can show an entire screen. You share your entire desktop. So to do that, you'd have to close this share and start a new one.
Yeah, that's what I'm trying to do actually, and I'm not even letting me close it. Let's
Normally
see what's
you do
going
that at the top of the shared screen.
Yeah, I'm looking at it. Let's see, new share maybe. Okay, stop share. Okay.
There you go.
So
Yes.
now I've stopped it. So
Yes.
if
we're
I
back
click
to
on
you.
share screen, then. Okay, let's see how this is going to work this time. Okay, is that better? Can you see my screen now?
Just a moment.
Yes.
Yes. Yes, I see your entire desktop with that.
Okay, let's see if I can handle it. Let's see here.
But it's quite visible. You could make it a little bit deeper, a little bit longer.
Okay, I'm trying to. Okay, so is everything, can you see it now or is anything wrong? Can you see? I'm on screen number
Nope.
1.
Yes, I see a rectangle that's relatively limited in height. If you could increase the height of the window, it might make it a little bit better, but it's completely readable the way you have it right now.
Can you see page 2 now? Is it going through the
Yes.
pages?
Yes.
Okay, maybe it's all right then.
Otherwise, you have to enlarge the original.
Yes. Yes, that's better.
Okay, so I'm on page 1 now, geometric isocalculus. Well, here, so in this line, I say to define an isoreal number, what we're basically doing is we're multiplying all the real numbers by an iso unit that we choose. So I'm also defining the notation R hat. That means whatever real number you have, when you put a hat on it, you just multiply it by the iso unit. And that's in the base geometric. So in this case, just for real numbers, we're just really mapping the real numbers into the real numbers times the iso unit, the new iso unit. Okay, so that's the operation I'm also defining. Hat means, if you put a hat on something, it means whatever that element is, just multiply it on the right by the iso unit, which I'm denoting by I. Now, then I want to define what I call a special unit, which is star, which is just exactly the element P, or the inverse. In this case, we're just looking at numbers, so it's just the inverse of that real number then.
You call it a special symbol, but in fact, it's just an element of the algebra, correct?
That's right. It's just a special notation for that symbol T, which I'm going to use to define the iso real number system then.
So that differs from the notation that was used by Dr. Santilli and by Dr. Georgiev, in as much as when they write the symbol star, they're referring to a new operator, not to an element
Yeah,
of
and-
the algebra.
That's right. My reason for doing that is because I want my product just to be my, what do you call it? Superposition, not superposition, but just adjacency. So you don't have any
Mhm.
symbol for multiplication, just, you know, A times B is just AB, where it's understood that you're
And that,
multiplying A times B. So for the,
that took
for the-
me a little while to understand what you were doing, especially in equation number 2, right? Because that looks like an operator star, a binary operation star applied to 2 isoelements. But you're saying, don't read it that way. Read this as an element of the algebra times the algebra of an algebra times another algebra element.
yeah,
of
that's
the
right.
algebra.
So so look at equation 2, you see
Yes,
exactly.
a binary operation, no? We need to see a binary operation. Yes.
The only binary operation that he has is
Nine.
geometric algebra multiplication.
Yeah, I'm
In the
referring
base-
everything back to the base algebra, in this case, just the real number system. Then. So when I write A hat star B, I mean exactly what's immediately to the right of that. AI, that's because of the hat on the A. And then 1 over I, that's the same thing as a star element. But you see, you can think about it as a binary operation, A star B, but actually to define that in the base algebra, you're using a number of different products. You're using A times I, and then 1 over I, that's the star, times B times I. And then you see then that's AB times I, and that's what we call AB hat, because that means take AB and multiply it on the right by I, which is what we have here then. Well, again, that's just so all our operations are really translated immediately to the base algebra. In this case, it's just the real numbers, but I'll do exactly the same thing with the Clifford algebras, geometric algebras.
If I may have a comment, that's the subject, as I indicated to you in our exchange. This is very intriguing because particularly from an abstract viewpoint, because when we go and correct me if I understood correct, if I understood properly, because in isotopy the star product is a real product. You know, it's different than the ordinary product. While in this star product that you define, it's very intriguing for me because the end result is identity. R star or I is equal to R. So from an abstract viewpoint, it's an identity. But however, if you look explicitly what it is, you see the topic element. So I think this is very intriguing indeed.
Yeah, so I am trying to define the binary operation, but actually I'm doing it in the base algebra, so it's more complicated. In this case, we're just talking about real numbers. So
You can
Are you familiar with the notation that Lashevich used of like representing operators in terms of what he called string diagrams or something like this? You know, where you write a binary operation is if I don't want to go too far off on a tangent, but how can I if I would like to annotate this somehow? Oh yeah, okay.
I'm not sure exactly what that is actually.
So can I do this? Yeah, okay.
But anyway, as you can see, the addition is just ordinary addition of real numbers. There's no change in the operation of addition. And that goes over when we go into Clifford algebras. It's the same thing. It's addition is always the same as the addition of the base elements. So there's no problem with addition being it's exactly the same addition as for the real numbers. And so don't introduce another symbol like a hat on. It's plus. It's just like with real numbers, or in Clifford algebra, it's just the addition of geometric numbers. Addition does not change in the algebra, just the idea. Of course, you could define an iso algebra where you're actually changing the notion of addition too, but then it just becomes much more complicated to do that.
But in the base algebra, you were treating this star as an element, right?
Well,
And
I'm
so
thinking about it when I write equation number 2, star is the operation, but actually, when we refer it back to the base just real numbers, it's the product of 3 real numbers. A times the unit, times the I, times 1 over I. And of course, that's why it reduces to AB hat. Well, you can see, I call it just AB hat because that's in the iso real numbers. And I can drop the I, then I don't need the I because that's an iso unit. So,
but this, at first glance, when I look at that, I think, well, that's kind of like a convenient accident, like it's symbolically convenient, but not fundamentally what's going on.
well, this idea of the hat operation, you can see in that last on the right there, it's hat AB, and that's in R hat. So that's the iso real numbers then. And it's just
I agree. It's interesting.
But if I may have it,
it just simplifies things. Rather, I get confused with all the hats and the stars and everything. It becomes very confusing, and for the
the confusion is that you use the symbol star. You see, you introduce a multiplication that is structurally different than what has been called a star for many years, decades. So definitely I would recommend you to introduce a square, for instance, or a dot, a black dot, any symbol except star. For instance, you will not use in a paper do this operation and then the trivial part, it doesn't mix with applications. I don't know. It's a new operation, therefore you should introduce a new symbol. It's a very interesting new operation, but
well, yeah, that's what I'm calling it. But actually, the multiplication is defined by a particular element of the real number system. That's all. It's 1 over the iso unit.
that's true.
So everything is defined there. The first equation, A hat star B hat. Okay, the A hat means you multiply A by I, and the star means just 1 over I, and the B hat is BI. So I don't know, it seems like it's the most efficient way of doing that, as I see it.
I think what really makes it very interesting and powerful, I think, is that you're showing that you can do exactly the same thing in Clifford algebra. And so that
Well, it's exactly the same rules apply immediately. Nothing's changed then. So it can be in any algebra, in fact, not a Clifford algebra, more general algebra than that, maybe a tensor algebra even, I don't know. I haven't really tried it more generally than that.
Well, but if you look at the original papers about isopity and algebras, they would not limit themselves to sort of multiplicative operations, right? So that you would map f hat or a hat into f of a, right? And you would map b into g of b, right? And then, so the at the abstract level, we're only talking about mappings, and here you're talking about a particular choice of multiplicative kind of mappings.
But are we talking about, when you talk about isotropy, is that the same thing? Are you referring to isomorphisms of algebras? Or isotropy is, what does that refer specifically to iso algebras when you're using the word isotropy? I'm not sure exactly.
Well,
Isotropy.
the general definition of isopity is in terms of any kind of mapping. Like, it doesn't necessarily have to be like multiply by I. It could be, F of.
So that is like an isomorphism then, I suppose, like group isomorphism.
Well, then in order to define multiplication, you need that the mapping F be invertible. Right?
Yeah, so.
But here we are only at the real numbers level. That's right.
It's just real.
Only that. And I think that there is no problem with the definition here, because you are only using the product by I, and then all of this works okay, I think.
Well, yeah, actually, you could just look at it as a first A hat star B hat, then take the last one is equal to A B hat. And that's it then.
Yes.
Indicate with your pointer so I can follow you. Can you see my pointer?
Where is that? I don't
Yes.
see anything.
Yes, I see your pointer moving.
This is
Okay, that's my point. Yeah. Oh, I see what you're saying. You want me to, yeah. So this is the first A hat star B, and then the last is A hat, A B hat. Well, that just means multiply by I then. So that's,
my point is this operation here, defined here, the star here it produces an identity. It's structurally different than the star. That's why you should use for this operation here. You cannot use the same symbol, at least it's confusing. Because you see that this product is not A, is a completely different result. And if you use this definition, then this should be an identity. It is not an identity. You see, A hat star B hat is not it's not an identity. So this is my mind.
Well, no, but it is an identity. In fact, it's even a syntactical identity, right? That we map them like element by element.
yeah, A hat means A is I, and star means 1 over I. But of course, this is product here. This is the ordinary product of real numbers that we're looking at right here. Yeah, yeah. I'm really trying to be identical with what Dr. Santilli is saying, that it's just another way of defining exactly the same product. A nice real difference.
But this reformulation is intriguing from an abstract viewpoint, because you can see that here is the identity. Isomorphism multiplied by the inverse. It is a trivial unit, but you look at the structure, it's not the trivial unit. So, from an abstract, it's a way to render isotopy part of an abstract formulation. In other words, let me put it in a different way. I have no knowledge, no way in which I can express isotopy at the abstract realization of free level. This can will instead will allow this operation here will allow indeed to represent isotopy at the abstract level. But then whether I have problems in identifying this star operation with this one, because the results are different. But if
well, the interesting thing is, if you let I equal to 1, then of course it just reduces to the ordinary product of real numbers. It's just times 8. So it's just the ordinary real number system.
Oh yes, of course, yeah.
Okay, well, we can go on and look at it, how it works with the geometric algebra then. So it's exactly the same thing that I'm doing for geometric numbers. Geometric algebra G3, okay. So we've gone through this before, but the standard basis of geometric algebra of Euclidean space is just spanned by E1, 3 unit vectors, E1 orthogonal unit vectors, we say they're orthogonal because they're anti-commutative elements. And then you have the product of those orthogonal elements. E1 times E2 is a bivector, E1, E3, and E2, E3. And then, of course, the pseudo-scalar element is a trivector, E1 times E2. This is the geometric product.
But Garret, wouldn't you normally just write this as like, instead of writing E1 times E2, isn't it more correct to write, say, E12?
Well, that's what I do right
E1,
below that. The quantities E1, 2 is just equal to E1 times E2.
Yeah,
minus
yes, well, the point being that E12 may not be just the product.
Well, yeah, in this case, I say they're orthogonal vectors, so it is it reduces to, it is
So
orthogonal.
you've assumed some sort of primordial basis in some way.
No, that's right, orthonormal basis. So an orthonormal basis are anti-commutative unit vectors which generate the basis. So that's what I say here. E1, E2, E3 unit vectors along X, Y, Z axis in the coordinate space R3. So that's usual orthogonal. So the anti-commutative, and that's why I can define the quantities E1, 2 is just this then. And then we can check that if we take the bivector in the XY plane, that's E1, 2 squared. Well, that just means E1 times E2, E1 times E2. They're orthogonal vectors, so they're anti-commutative. So we get minus, it's associative algebra, minus E1 times E2 times E2 times E1. Okay, and they have square 1, so you can see a unit bivector square minus 1 in the Euclidean unit bivector.
But I guess my point was that you can describe the structure of the Clifford algebra without referring to the products of some elemental basis, right? So it's sufficient to say that E12 squared is equal to minus 1.
Yeah, well, of course we get this cross algebra where, of course, all vectors are anti-commutative by definition. All non-zero vectors are not equal vectors anti-commute in the Grossman algebra. But here we're assuming that's right. Clifford algebra, you need a metric. A Euclidean Clifford algebra is defined for R3 Euclidean 3 space by choosing orthogonal vectors which have square plus 1 and anti-commute them. And we can think about those along the XYZ axis. So that's right, a general geometric product you decompose into a symmetric and an anti-symmetric part, which is what defines the signature of the algebra. Okay, so so anyway, this is orthonormal basis. Try to keep things simple as possible without.
Subject, allow me to ask a question maybe out of this field, because you speak about you repeat about symmetric and anti-symmetric. This reminds me of the admissible algebra, because the admissible algebra are composed of the symmetric part, which is Lie, and the symmetric part, which is Jordan. So the question, can the Clifford algebra provide a geometric representation of a better geometric representation of the Lie admissible algebra? Because that's irreversibility, and for us, that's the ultimate mathematics.
Yeah, well, normally people start with perhaps introducing the Grossman algebra, where you're not assuming the existence of any metric or a metric space, and then you just have anti-commutivity. Of course, the Lie algebra just as a Lie algebra of vectors, and they're anti-commutative then. So, so here, if we go down to equation 4, that's the what I call the spectral basis, and this is where you have U plus minus equal to 1/2 1 plus or minus E3, where they're mutually annihilating idempotents. which satisfy these rules here, u plus times u minus. Well, it's simple to calculate it. Just you can do it on paper, 1/2, 1 plus or minus. If you say 1 plus E3 times minus E3, you get 0 because 1 squared is 1. And then you have minus E3 squared, so you have minus 1 is 0 then. Well, then you use the rules for those idempotents. They're mutually annihilating. U plus times U minus is equal to 0. U plus U minus is equal to 1. And if you look at E3, if you multiply E3 times this, you can see it reverses the sign. So E3 changes, absorb E3 if you just multiply it by E plus, and then it changes the sign because you can see E3 times U plus gives you 1 plus E3 squared, which is 1. So it's just U plus. But if you change this, you go 1 E3 times U minus, then you get 1. Then you get 1 minus. Well, yeah, that's right. So it just changes the sign of everything. It gives 1. What am I doing here? Yeah, I multiply by E3 times, you get E3 minus 1. Okay, so that's where it changes the sign of the idempotent. So that's this expression here. Okay, and then I define then the matrix of A is just A11, alpha 1, alpha 1, 2, the usual standard 2 by 2 matrix. And in terms of this basis here, this matrix interpreted as an element of the Clifford algebra is just A11 times U plus A12 times U minus, which is the same thing as this, and A21 times E1 times U plus this element. And so that's why I call it the coordinate matrix of the Clifford number with respect to the spectral basis, which is defined here then. Okay, and then we can see how we get the Pauli matrices. It's just the usual matrices 0, 1, 1, 0, I, my. Of course, the interesting here is that I now is the unit trivector. It's E1 times E2 times E3. So it's not just the square root of minus 1, but it's the square root of minus 1 with the interpretation of being a unit trivector in the algebra, which adds geometric interpretations to the square root of minus 1. But of course, a bivector also has square minus 1. Okay, well, I'm just representing here E1 in terms of the spectral basis then. And now I'm just making the identification of the Pauli vectors with just the usual, that's the standard basis I use is just the Pauli vectors. So I identify sigma k with EKs. But of course, the matrix is really the matrix. These are the Pauli matrices then. So I'd have to put sigma 1 in here for this notation to distinguish clearly between the vector, the Pauli vector, and the Pauli matrix of the vectors, which is E1, E2, the 3 matrices of the Pauli algebra then. Okay, well, here then we have given a geometric number in G3, it takes on this representation, alpha 0 times, well, of course, now G3 is defined with the I, which is equal to E1 times E2 times E3 then. And the determinant of that is just equal to, if you go ahead and take the determinant of this, you'll see you get E0 squared minus alpha 1 squared minus alpha 2 squared minus alpha 3 squared. So that's just the standard definition of the algebra G3 in terms of 2 by 2 complex matrices. But now I has the interpretation of the unit trivectors in the geometric algebra then. Okay, so now I want to define an iso geometric algebra. And again, it's so So now I'm just letting I be any invertible call it the ISO unit I. And I'm defining again star equal to the inverse of that element. Geometric algebra, in this case, E3. That's the algebra. Well, this can be for any geometric algebra, but I'm really restricting our attention to the base geometric algebra G3. So it can be, the ideas can easily be extended to any geometric algebra GPQ, where PQ is a signature of the quadratic form, which is usually used to define the Clifford algebra of that signature. And again,
one point of clarification, that the inverse of I, in this case, where I is an arbitrary element of the algebra, of the geometric algebra, does that cause any, uncertainty? I mean,
no, actually, you can take it back to take the inverse of the geometric algebra is exactly the inverse of the geometric matrix that corresponds to it. So you can take the inverse of this matrix here then, and you get exactly that.
So in spite of the
as
fact
long as it has an inverse.
but the
Of
geometric
course, it
algebra,
determines equal to 0, it doesn't exist.
yeah. So
that's
the fact that the geometric algebra doesn't have, or well, does have 0 divisors, for example, doesn't interfere
Exactly.
with. It doesn't interfere with this
Well,
definition
what
of
determines
inverse.
whether it's 0 divisor or not is whether the determinant of the Pauli matrix in this case is equal to 0. All the other elements have, are not, they're all invertible as long as the determinant is not equal to 0, which is the advantage of thinking about the complex matrix, 2 by 2 matrix of a geometric number. It's just the usual Pauli matrix, the complex Pauli matrix.
But if I turns out to be, if I was turns out to be a 0 divisor.
No, the I is not a 0 divisor. It has square minus 1. And it's in the center of the algebra, so it commutes with all the elements in the geometric algebra. Just as I equal to square minus 1 is assumed to commute with real numbers.
Well, when you say an invertible ISO unit, that means immediately that I is not a 0 divisor, right?
Yeah, it just means that the determinant of that element is equal to 1 when you write in terms of its Pauli matrix.
But it's broader than the ISO unit that we use in our field, because an invertible ISO unit can also be a complex value. While mathematically is fully acceptable, absolutely, I have no objection. Actually, it's the correct way of defining a unit, because
this is equivalent, I think. This is equivalent because I could be
could be any element
trivector,
right? That has determinant not equal to 0 in terms of its Pauli matrix.
Yeah.
So it could be the small lowercase I that you referenced above.
That's right. The lowercase I has exactly the same properties as I squared equal to minus 1, but it's given the geometric interpretation. I is a unit trivector, and that commutes with E1 and E2 because you have 3 vectors. E1, E2, E3 will commute, anti-commute 3 times with any elements. It's in the center of the algebra. I is in the center, which means it commutes with all the geometric algebra, which is exactly what I does in the Pauli algebra. But I in the Pauli algebra is usually thought of as just the square root of minus 1. But in this case, it's actually has a geometric interpretation as a unit volume element or trivector of the algebra. Well, if we look at what it becomes in the geometric algebra, you can represent it as the element I as a complex number, or the same thing as a real number plus a a pseudo scalar or trivector plus a complex vector. Well, what is a complex vector? Well, it's actually Z defining it equal to a vector, just a usual vector in three-dimensional space, plus the dual of the three vector. Okay, well, that's different than the polyalgebra. If you're thinking about I as a square root of minus 1, we're interpreting I times Y to be a bivector, and that's why I'm saying 1 plus 2. So it's a vector plus the dual of a vector, or I times Y is plus a 2 vector. So a general, and that's what I call a complex vector then. And it's invertible when I times its reverse, if you want to think about that, is equal to alpha squared minus Z squared, not equal to 0 then. So that characterizes all non-invertible elements in the Clifford algebra, or as a polymatrix, just says the determinant of the polymatrix corresponding to that is non-zero then. And we say it's positive definite if its determinant is positive then. I think that agrees with Dr. Santilli's definition of positive definite too. The determinant is positive.
For physical application, because for a complex value for actually you only represent forces, and complex value forces don't exist in nature, so that's why we don't. But again, not to repeat, but from a mathematical viewpoint, definitely I recommend the definition that you adopted, Dr. Sobczyk. It's enough to be invertible to do everything. So why to be positive definite?
Okay, so here again, so exactly the same definitions we use for the real numbers. I find given any geometric number, when you write a hat over it, I mean by that you multiply whatever that geometric number is, you multiply it times the ISO unit then. That's all I'm saying in that equation there. And then again, I take addition in isogeometric algebra to be exactly the same thing as iso addition of the same addition as in the Clifford algebra then. So I don't have a special symbol. I don't write plus hat over it because it's the same addition as in the base geometric algebra, which is just G3. And again, so there you have it. It's A plus B times I. And of course, if I just write hat over all that, I mean multiply that number by I then in the base geometric algebra. So I'm trying to clearly relate addition and multiplication of iso numbers to the corresponding operations in the base algebra, in this case, base geometric algebra. And then the same thing, I use a special element, which I just define to be the inverse of the I, to define the star multiplication in the isogeometric algebra by the same equation I used for the real numbers, and no difference at all. It's equation 9 and what I previously wrote for the real numbers, but now we're in the isogeometric algebra. So the element denoted by AB hat is just the product of A times B in the base algebra times the iso unit. So this saves a lot of notation. Otherwise, you have to take each element and multiply I times it. It's much easier and much clearer, I think, just to write it in this way. So you avoid having to always.
There's no question. It's very elegant and new and very, very nice. No question about it. Indeed.
I hope it's not really new. I'm trying to really be as close to your notation as possible, but I'm thinking about it a little differently. That's all.
You can introduce any notation you want. There is one point that may be of interest to you. I see the connection with this presentation. Namely, for us, for a scalar has to be an element of the base field. Now, for when we do an isotopy, the scalar, an isoscalar has to be an element of the iso field. So if you look at the invariant for Lorentz, for instance, invariant has to be multiplied by the iso unit. Now, when you do the limit of the iso invariant in the conventional space-time, then you end up, of course, you recover the conventional Minkowski, but then you need necessarily the multiplication by 1. And therefore, we need what we have to do. In reality, we have redefined conventional numbers, a conventional field of real numbers, just by multiplying every number by the number 1. Well, there is a beautiful connection with what you present here, because this multiplication of ordinary number by the number 1, you look at at the structure of the number 1, what you say very originally, the number 1 is as a structure because the product of the actually you only multiply by this inverse. So this in a way, what you present is a unified is a representation of isonumber that we use not only at the isotopic element, but we use at the conventional number level.
Mhm. That's right. Yeah, you might want to look at this equation here. I can actually write I hat star hat. By star hat, well, again, star means I inverse times I, and of course it's equal to 1 then. So, but whereas if I write plus hat, then of course it's just the usual. So I don't multiply that. I don't want to use my iso addition is just identical to geometric addition. So I never write hat over the plus. So but star, remember star is just the inverse of the iso unit. So I am able to write star hat as, well, the inverse of the iso unit times I, then is just 1 then. But now look, that's a confusing thing with Dr. Santilli's notation. If I write I hat, that really means I squared, and not the same. That's not the same thing as the iso unit anymore. So that is a little confusing comparing it to Dr. Santilli's notation. I hat is his iso unit, but I hat for me now, I'm interpreting that as I squared because of this notation. Hat means multiplying whatever the element is by I. So I hat means I squared then, but I squared is not the iso unit any longer. Okay, so here it is then. We have G star I. Well, that's just equal to G times I inverse, because star means I inverse times I then. Okay, so you get G then. So that proves that I is the iso unit in the isogeometric algebra. But notice here, I just G be any element of the isogeometric algebra. I don't have to put a hat on it, because all elements and the elements of G3 hat are exactly the same elements multiplied in the base algebra multiplied by I. So G is just an element of which just means that G is then also G3, because the elements of the iso algebra and the geometric algebra are exactly the same elements, just like the real numbers and the iso real numbers are all real numbers, except the real numbers are scaled by the iso unit. So in a certain sense, we can think about the iso unit as scaling by an element in the geometric algebra, which has an inverse, any element, to find the scale, the new scale, or the iso unit of the geometric algebra then. Okay, so then this is just using the iso bases, and it's the same idea. You just put hats on the iso elements, and that's the same thing as the iso spectral bases then of the isogeometric algebra. So, okay, but now we're looking at the symmetric and asymmetric parts. So we say symmetric part, 1/2 the asymmetric part. Well, it reduces down to just the usual dot product of geometric numbers and the outer product, or the Grossman product, if you want to think about it that way, times I then. Well, okay, and then I put the star dot, and this thing. It's just extending the operations of the symmetric part with respect to the isogeometric algebra and the isoscalar product and the isogeometric exterior product, which I'm putting
That
star
could
on it.
perhaps be a bit confusing.
Yeah.
That
yeah,
notation of putting the star above the dot is,
yeah, that's true, but I think it's clear because the star represents the special element which defines the isogeometric algebra.
No, no,
It's the inverse.
but you
of it.
didn't define star as an operator, though.
No, that's true. That's true. But I'm defining star, put a dot star, the inner product star. Well, I have to distinguish it somehow because I need to write it as
it's okay.
times I.
It's
Why
clearly,
not just dot? Like,
but it could also be the case, yes, could also because the dot is a,
Okay, I suppose we could just extend the meaning of the dot product, but yeah, that's true. We could just do that, but
just a new product. You introduce it for the first time, so will be the dot will be okay.
well, of course, now we're back in the real number system here. When we look at that's just the real number system there, and of course here is that's the outer product star. So I'm just trying to keep it straight actually, but I cannot understand until you get used to a notation. It's always confusing.
That's okay.
Okay. Of course, the most interesting thing is to correctly define. Okay, so let's look at the geometric isocalculus. I'd like to say at least a couple of words about my special points. Okay, so G hat then I guess is the usual thing, but now I'm extending it to include functions, differential and integral operators. That's where the confusion arises for me even. Okay, so given a function which takes, say, x into f of x, so it's a mapping of a vector, in this case, into the geometric algebra then. So I want to lift that function to an iso function. I lift it simply by putting a hat on it. I mean f of x times I. So it's an extension then, but notice I don't put the I inside. I multiply it out. I take the usual function defined in the geometric algebra and multiply everything by I then after the operation. If f of x in the usual geometric algebra times I then. Well, again, because we have these properties here. It's it's just x dot y plus x wedge y times I. So that's reflected then also in the definition here. I do the function and I multiply times I. Okay, for example, the exponential function becomes the usual exponential function of a geometric number times I. The same thing with trig functions. Hat cosine G is cosine G times I, because essentially we're moving the iso product by just factoring out the I at the end then, rather than doing it with, the exponential function is just usual exponential, or for cosine, it's the cosine series for an arbitrary element in the geometric algebra. But now here's where we have the trouble. When I define D and the integral operator, these are functions as well, but I prefer, rather than, in a certain sense, this is D operating on the function f of x. So you might think that we should define it as D of f of x, everything times I, but then we also have the problem, usually with the differential operator, it operates on everything to the right. So that's the question. How do I really want to define that? So I want to multiply that D times I inside like this. And well, if I do it like that, then here, then you can see it, then I just get D f of x times I here, because f hat means multiply f of x times I inside. And the same thing with the integral operator. So
but until Excuse me, but until now you are using hats like a product by I. And here
Well, that's
you
right, on the
are,
right.
yes, and here you are changing the definition.
Yeah, that's right.
with
That's right. So this is where the confusion arises, even for me. I know that Dr. Santilli wants it. I think Dr. Santilli wants to write d hat as t times d, and the integral as t on the outside. So, you know, that's the,
only recommend that solution is one of the infinite number of possibilities that verify the axiom, what we call the axiom of d hat x hat equal to dx. You know, that's the axiom when we cover when the diagonal unit is a scalar. So, but here you have a beautiful new definition. So I see nothing wrong because I suspect there are many more.
But
yeah,
I
well,
think
that's
you
the
have to
thing.
be very
It's
careful.
really a matter of conventions that we're talking about, I think, more than anything else. How to make it least confusing. That's my concern. I don't like
Well,
when we write
but you
a
have to-
slash, for example.
But once the definition are correct, there is no confusion. No, once you define properly, I see no confusion.
Yeah, that's right. So we can, for example,
no,
define it as I say, d hat, put it inside, because then d is going to differentiate it as well. And the same thing with the star inside the integral. But that's a little different than what we used for the functional definition, which was hat of a function means you take the function and then you apply it to x and then multiply it by I. Well, I have a couple examples here. Okay, here x hat.
but the most critical thing though, the most critical thing here is Leibniz. I mean, if you're going to say that you have isocalculus, you want the d hat operator to be a derivation in the algebra.
Yes.
Yeah.
That's
right.
And,
Well,
and here this don't work.
Well, that's right.
Doesn't work.
I think this is what, that's right. I do prefer these definitions right here, because then it's still a derivation, because it's just defining it. You take f of x multiplied by I, but if you want, you could define it like, well, I'm not even sure how you want it. I think we want, do we want it? Okay, but notice that if I define it as I have it defined, then if I take d hat star f hat, then it becomes exactly d f of x times I then. So that's well defined.
But you need to write d hat of a hat star b hat, and you need that it be equal to a hat times d hat of b hat, right? Plus the other term, right? Plus
well, if I put a hat on the x, that means it means x times I. So I have to be careful. Let's see if I have.
Yes, I think it's tricky.
So that's the thing I don't want. Really, when I define f hat, I keep the I on the out. I take the function first, apply it to x.
And in this definition of your function, I think that it is different that was presented by Dr. Georgiev, because he put head not only in the symbol of the morphemes, but in the arguments too.
No, that's right. That's where it becomes confusing. Right. So you see, I want to keep that separate because I want to define f of x in the geometric, well, in the algebra. So I carry out that operation and multiply it times I at the end. Then I don't have to put all the inside. If that's the exponential function, then I have to indicate, that's the whole problem.
The main misunderstanding here. This is a very particular definition that applies only because you select. It is absolutely not the general. The general definition, and indeed, it's very easy to prove that does not apply to the exponential. The general definition is necessarily, as Dr. Cruz said, has to be, you have to also put the hat on the argument. If you put the on the argument, then you obtain that this applies universal also to the exponent. See, the exponent, in the exponent, there is the necessary emergence of the isotopic element in the exponentiation function. There is the appearance of the isotopic element in the exponent. There is a fundamental evidence for nonlinearity. And this definition does not apply. So I will not recommend you to use this definition unless you clarify, which you can do, of course. This is very, very special, applies only in certain cases. Is the definition that you will select, and you already, nobody can say no, that you will select, but it's not a definition of an iso function. No, I have to disagree on that.
Yeah, well,
Because the problem is called, we try to formalize iso mathematics. We need one formal definition of the operator head. And then we have to apply systematically in all the place. Then I don't know if okay, we are speaking here about one different definition of the operators, and I don't know if we still again in isocalculus, because we are changing here this.
Well, that's the thing. If we take an ISO unit for each separate dimension, then things really that's right. This won't work at all. But you know, it is reflecting this basic property that this property here, that you can always pull the I out here. You see, for product between two
numbers, but not
pull the I out of the, rather than having to write the ISO product all the way inside for general elements.
That's occur for numbers, but not for a function, because the theory
Okay.
isotopy are nonlinear and you cannot factorize the ISO unit all the time. No, especially with function you cannot. Otherwise, it becomes Now, the problem is here is this definition is it's good for numbers, but not for function, as far as we know. At least that's what we have done. You need the hat inside.
Yeah. So for me, I'm just wondering. For example, in geometric algebra, we always write rotation and reflection, two-sided rotation and two-sided reflection. But now when you introduce a different ISO unit in every dimension, I'm wondering if you can't express that as a people. I'm not sure exactly how to do that. In other words, yeah, let's see if I can maybe write something on the paper.
The special ISO for each variable, no.
One thing I think that would make this clearer is if you defined a differential without reference to x, right? That when you say f is the function, that's sufficient. You don't have to say f of x. That's the function evaluated at x. But,
well, exactly.
But if you write d, df, it's df evaluated at x. It's not d of f evaluated at x, right? It's because the differential operator operates on the function, not on the function evaluated at a particular place.
Dr. Page, this is exactly what I did in the Randy Cohn paper in 1996. The d hat is equal to t multiplied by d. So as a definition of the differential. The variable
yes.
means, however, for the variables, the original variables remain. But that is only one solution, the simplest possible solution for physics. There may be other solution.
Yeah, so I do remember your work that you sent us You wanted that condition that D, what was it, dx, d hat
At x, yeah, the axiom.
is equal to dx.
That's a basic axiom I will recommend it, 1996. The d hat, x hat, has to be equal to dx whenever the iso unit is either a constant or a function not explicitly or implicitly dependent on the variable of differentiation. And that is necessary to have a covering of the ordinary differential calculus. Otherwise, you introduce a totally different calculus with no connection to, and also so the necessary covering of the differential calculus allows you a covering theory, namely a theory that admits the preceding theory as a particular case. So, and that reduces to what we said before, that D hat as one solution, I have to say over and over again, the D hat is T multiplied by D. But however, Dr. Sobczyk, you may be facing a new solution, a new realization of the axiom. I'm not sure at this moment, but it's possible.
But this notation T, is it equivalent to star?
Yeah, that's right. It's just a symbol, a different symbol for star. Star is a different symbol for T.
So using
That's
your
all.
notation, that what Dr. Santilli is referring to as D hat would be written as star D, right?
Yeah, that's right. With star, of course, you can just treat it as an element. So you could put the star outside if you wanted to. It's flexible notation there. You know, here I have.
Well, you have to be.
Star
You have to
D
be careful. The main thing is you have to be careful that the D is not an associative operation, right? So when you write TD, you mean T times D of something, right?
Yeah, okay. You want D to be a derivation. Still, that's right. So this is all right here. D is a derivation. D hat is a derivation. It's I times f of x.
Myself difficulty in understanding this expression here. Again, because the differentiation has to be an operation and it cannot be a product. So I have difficulty here. And
but usually operations are defined in terms of products.
But the differential is a different thing, a different notion.
Well, that's, yeah, differential derivation.
Operational function. And so you cannot use the product, the differential. You cannot extend this, for instance, to two differentials in different variables and so on, because they are all applied to functions. So therefore, the notion of differential, it cannot be separated from a function in which the differential is applied. To my best knowledge, I'm not a mathematician, I beg you. But that's just for knowledge.
Well, that's exactly why I wanted to make out these points, because there is some confusion that even I'm not completely sure these points are making.
Because in my opinion, can you go please a little bit up in can you move up? Can I see up in this transparency, if you don't mind, please?
Where?
I think the biggest difficulty is in here, because it's very, it applies to numbers, very, very few, and the very, very elementary, I don't know, no functions that will apply, very, very rare function, no. And then can you go down, please? Can you, the next page, please?
You want 13, right?
This, for example, here is good, I think.
That's it. Can you see, this is the biggest, generally does not apply to functions. And this is my biggest difficulty. And then here I have a serious difficulty in understanding this operation applied to, it's not a differential. I'm not against those objects. No, misunderstand. Only that to clarify that it's not in the conventional definition of what a differential is. Remember, I said to preserve the original idea. So if we have, if the for an isodifferential to be an isodifferential has to be a differential first, and then has to have the same action.
So maybe we should just define D as just the usual D. Why do we even have to change the definition of D for?
Because it's not a conventional differentiation. Otherwise, you have Newton-Leibniz. Absolutely. Necessarily, you have to generalize the notion of differential. And indeed,
Well, maybe we should define differentiation just as the usual difference of a f of x plus dx minus f of x divided by dx, a limit, the usual limit, and see how it would come out if you did it that way, maybe.
if you look at volume one of elements of hadronic mechanics, you will see the difference in details. Yes, it's just different. It's a different operation. Different than the conventional definition of differential. No.
But I think it's correct, Dr. Santilli, what you're saying is that the issue starts here at this definition 13. Like when you write f hat of x, the hat is operating on f. It has nothing to do with x, right? So if you suppress the x altogether, you want to write f hat is defined as something involving f.
So it's two functions we're talking about. You're talking about f of the quantity x, and then it's a composition of hat with f, the rule f. So, but applied to x.
But you have to completely forget about x. Like x has nothing to do with the issue. It's only what do you mean when you write f hat?
Well, I think it is, f is a rule, and f hat is a second rule applied to the first rule. So it's a composition of f with hat. So it means then f of x, and if you put, well, for example, when I do it here, there you have it.
But that's really tricky, right? Because you would like f hat to be fi.
Well, that's right. Well, you can see with the exponential function here.
But
that's what I mean here too.
No, but again, forget about x. X has nothing to do with what you're doing here. You need f hat to be something involving f, but your point that you made at one point is that in geometric algebra, elements can be considered operators, right?
That's right.
And that's fairly important. So that means something like if
in fact, any linear operator can be expressed totally in terms of the geometric product.
Yes, and that's quite
right.
significant because the derivation is a linear operator.
That's right. So that's right.
But unfortunately, functions in general are not corresponding to being.
Okay, but let's look at 13 for a second. If I just, instead of wrote a small hat, if I wrote a big hat over it, just like I do with the exponential function, then it's clear exactly what I mean. You apply f to x, and then you apply hat to the resulting expression. So exponential g hat means take exponential of g and then multiply by I.
Yeah, but those are.
I think that we need to clarify here what is the meaning of head acting on composition.
Yeah, well, that's what I try to do.
Because we can take x like another element of in the algebra, and then we have here one composition between two elements, and how act the head operator on this.
Well, yeah, it's a composition of two functions. First,
Yes. Mhm.
apply exponential to g, and second, apply the hat operation. So then it becomes exponential g times I. It's
but-
just a so maybe my notation should be a big hat over f of x, because I mean composition of f with hat. Well, so I take first apply f to x, and then I apply hat to the result of that, and I get
Yeah.
f of x times I.
But then you're no longer defining iso function.
No, there's nothing,
No,
not
it is.
higher
It
form.
is defining. That's what I call an iso function.
Iso exponent. No, there's exponent as the isotopic element in the exponential term, and this does not. See, no, this is no connection with iso function. I mean, you can do it, but let me clarify. This is what you assume, and those are what the consequences. But this is no connection with iso function. It's not applicable to the isosinus. For instance, and you lose. This is it from a physical viewpoint. It's trivial because it's linear. You lose the nonlinearity that only occurs when the isotopic element is in the exponent of the exponential function, or in many other situations. So this is a linear theory from a physical viewpoint. I will be sure mathematically it's interested, but I will see is within the class of isomorphism of conventional quantum mechanics. There is nothing new as compared to quantum mechanics because it's linear. So
Well, it is confusing, that's for sure. So,
No.
yeah, well, I like to see it.
you make it, you're as a mathematician, you assume you make a definition, anything you want. The definition is very clear. This is what the
But aren't we just composing functions? I can't see how we're doing anything but composing functions here.
no, this is you're allowed to do this as the definition. You have this consequence and you have this consequence. You are perfectly allowed to do that, but this is not no connection with isotopy. And I will the only problem, the only questionable point is that the theory becomes linear, and so you lose the nonlinearity of the isotopy. It's fundamental to do any new physics. Fundamental. Otherwise,
No, but this linearity doesn't change in isogeometric algebra, iso real numbers, linearity is 30. It doesn't change the concept of linearity. And in geometric algebra, as I said, any linear function can be represented entirely in terms of the geometric product. So yeah, I'm still a little confused, I have to say. So I'd like to see, again, I'll go over what you wrote before and try to understand exactly where the problem is.
I think
your
that-
statement is interesting because you just
Yeah.
said that it doesn't change the concept of linearity, and that isn't clear to me.
Yeah, well, it's a strange definition of isotropy, where iso algebra just multiplied by an iso unit. It's pretty strange, but I never thought about isogeometric algebras before. But I think this basic formula 13 is important because you don't, like for example, the dot product and the wedge product, seems to be, again, multiply everything by I in the base algebra. That seems to be very important, the definition of the iso real numbers even. That's the same thing we had here at the beginning. A hat is A times I for real numbers, and the sum, okay, the same. And number two, the same, exactly the same in the geometric algebra. So, okay, if we define differentiation integration, which is real numbers, and I would think that, yeah, well, anyway, I tried to.
Well, suppose we define, say, f as just being the square. So like, suppose f was, x squared, right? Then
Okay,
we do hat of square, what do we mean? What are we doing? Right? So we have your example 13. Suppose just take f is
It's applicable to
square.
type of scalar. X square is a scalar. So it is a definition of for scalar, yes, for all of them, yes. So
No, but Professor Page are saying that x squared is x star head x.
That's right. The idea is you can take out the I, you can factor it out at the end. That's the whole idea.
yes,
And you can do that in geometric algebra or in real numbers.
for scalar, yes, it works. Yes, indeed. It's
But for non-scalars, it works as well. That's the point. Matrix multiplication, you can take
that
the
I,
I for matrix multiplication as well.
because of this expression here, I'm not sure. Yeah.
I think that here the idea is that we are in the scalar field of functions. We are in scalar field of functions.
Of course,
And then we need to define here all the basic operation between functions that can to think about them like an algebra.
well, for example, if you take the exponential of a matrix, it's just the usual definition of the exponential function, but you're using the matrix product. Well, but that's the same thing. It reduces the product of in addition and multiplication of components of real numbers, but it's still ordinary multiplication that we're talking about. Well, that's the same thing in geometric algebra. There's no difference, like I say. Geometric algebra is isomorphic to the matrix algebra, algebraically isomorphic. So there's no real difference there, I don't think.
But that's because ultimately your unit is the number one, because it's equivalent to the number one. So what you said is absolutely correct, but it's a consequence that you change the rules, and when you rather than multiply by an iso unit, which is a matrix, you multiply by the number one, which is the product of a matrix multiplied by the inverse.
Yeah, but when you define the iso multiplication, you first put a t in there, and it cancels it out. So all the interior products cancel out, and you're just left with the I on the outside.
For numbers, yes, but not for function. For function, it is
For functions too, the same thing. If it's defined in terms of ordinary matrix multiplication, that's what you're defining your function in terms of. You can factor it out of the matrix multiplication as well, because the t cancels out, all the interior products go out of it. Cancels out.
The moment you can factorize everywhere the iso unit, theory is linear, pure quantum mechanics.
Well, anyway, that's, yeah, well.
The knowledge of the hadronic mechanics is that you cannot factorize the isotopic element out of the iso exponent. No, you cannot. So so that's intrinsically nonlinear theory.
Well, don't we have that the same, like you say, just take any matrix A star B. What do we mean by when we multiply a matrix A star B? What does that mean?
Well, if you're talking about matrix, is a different situation than function. Yes, a matrix.
But even the exponential function of a matrix is just defined in terms of powers of the matrix in addition.
But then again, we have please give me a moment of attention. First of all, we have to define what an isomatrix is. An isomatrix is a matrix in which the element code, for instance, could be isofunction. And then the result of this matrix, MA, with ISO function as element is multiplied by the ISO unit. So no way you can factorize no way you can factorize the ISO unit. That's the essence of the novelty of hadronic mechanics. Nonlinearity becomes intrinsically in the structure of the theory, and all this by using the axiom of quantum mechanics. That was very surprising for me, because I was not expected to salvage the axiom. Instead, the axiom are preserved. That's it, I think, is the power. But again, the basic problem that subject is here. It's okay for scalar. Sure, for scalar it's okay, but that's it. Sinus, for instance, will not apply. Then cosine, hyperbolic function. You can define iso hyperbolic function. This is a scalar expression.
Mm. Yeah.
Please don't accept my idea as being final. Just, I'm trying to give my wish to help you as much as I can. Certainly.
Well, as I say, I consider geometric algebra as the extension of the real number system to include the idea of, or the concept of direction. But you still have just an ordinary multiplication of geometric numbers. So if you define iso geometric multiplication, essentially all you're doing, again, you're preserving the anti-symmetric part, but the symmetric part is what changes. And so the iso Lie algebra is the same as the Lie algebra, because the Lie algebra is defined anti-symmetric products.
But careful, listen to me in your interest, because you use matrix and not isometric. You do not consider the iso product of the isometric. No, you consider an isotopic product of ordinary matrix, but that's not a full isotopy. You can do that. Don't misunderstand me. You certainly can do that. But don't consider that to be the final version. No, it's not the definition of an isotopy. No.
Okay, well, back to the drawing board.
You do a kind of a mixture of the two. On one side, I maintain the notion of matrix. On the other side, I generalize the product. You can do that. It's not a full isotopy.
But the examples you're giving us really involves just your notation. You write a matrix talking its diagonal elements. So you're really talking about matrices as well.
Because we consider in cases, our paper is based on this notion that we use ordinary matrix. We merely generalize the product into an iso product. We got a good physical results. My only point from a mathematical viewpoint, no, let's pass to mathematics. Let's formulate Clifford algebra in the correct way. That's not the way to correct at the level of the iso Clifford algebra. No, you have to iso has to be everywhere. In each individual item, matrix has to be an isomatrix, which is again is an ordinary matrix. Those elements are iso function multiplied by the iso unit, and then you will see the non-triviality. Then you will see the entire non-triviality while you preserve the axiom of the Clifford algebra.
But when you actually do calculation, you're reducing it to all the operations to the base algebra. Is that not true?
I'm sorry, can you repeat, please?
I say when you actually do calculations, you're reducing all your calculations from the iso algebra to the ordinary algebra, to the base algebra.
No. Only in the final eigenvalue. Only the iso eigenvalue. In other words, you look at the iso Schrödinger equation. On the right hand side is the iso eigenvalue isotopically multiplied by the iso function, and then on the right hand side, the iso unit and the isotopic element they cancel up, and you end up with an ordinary number, the eigenvalue multiplied by the iso function. But if you go on the left hand side, absolutely you cannot do that. No way you can. That's what we are saying. You cannot factorize the unit. Otherwise, you get linearity. As a final ultimate result, this was very important so that an equation, which is the left-hand side, non-linear, the equation on the left-hand side, can be reduced has to be reduced to an ordinary number for a theory, for any theory to be experimentally verifiable. Because the experiment produced ordinary numbers, not isonumbers or isofunctions. No, this is our representation. So, that's the power of the iso-Schrödinger equation, that after using, despite the using of non-linear, non-local, and non-potential forces, you end up with the final result, which is ordinary numbers. And that's why we believe in the experimental verification. But careful that this is only for the final results, but not for the process in reaching that result. No.
Okay, well, I have to go back and again look at what you've written, try to understand exactly what that distinction is better.
I think still that equation 13 or definition 13 is really very critical. And your argument sometimes it convinces me and sometimes it doesn't. Because I'm thinking I need an operation hat that applies to any given function. So if somebody gives me a function, I believe perhaps that it can be expressed in geometric algebra as some kind of expression with some unknowns, like some unknowns in that expression. And so when I write f hat, I need to operate on that expression, but I have to be careful.
I suppose the confusion would arise. I'm not sure. Like I say, I'm trying to reduce everything to the base algebra, and but
yes.
apparently maybe.
So when you write, so if f is, say, some arbitrary expression like a times b plus c, right? And we're saying the unknown here is b, right? So so we have an a and a c, and so when we think of this as a mapping from, if somebody tells me a value of b, then I can tell them the result of that expression, right? So when we operate on this function, with the hat, we need to be able to translate that into an operation on the expressions, the underlying expression that defines the operation. And as long as that
trying to use composition of functions, that's exactly what I'm trying to define it in terms of.
You need to reduce the notion of composition of function to some operation on the operations defined in your algebra.
Well, of course, that's what I do with the next expression for exponential hat. I mean, exponential.
Yes, because you can do that, because you can, in geometric algebra, you can express the exponential as a power series, right?
Well, with matrix algebra too, that's what people do, of course.
Yes, and so as long as you can express it as a power series, then you know how hat should operate.
Yeah. Well, but yeah, so that hat operation is well defined. Do the first function and then apply the hat function, which means multiply everything on the right by I.
But you have to, like, you don't multiply the sum of two things by I.
Oh, sure. Why not? In fact, that was the other expression here. Where is it?
But you said X, yeah.
Right here, look. A hat plus B hat means, well, again, you take the sum and multiply by I. Number 8. And okay, this one, A hat star B hat, Well, it's just AB because we're reducing everything to the base algebra. So everything, this other thing cancels out all the time. That's the whole power of the ISO definition of the ISO algebra as I see it. And then that means AB, where AB is the geometric product in G3 hat. Well, that's what puts the I and takes out the I. And well, anyway, that's.
So
But again,
you can take any analytic function then has this
exactly. It
form.
works for any analytic. Maybe that's what we should say. But what kind of functions are we dealing with?
Mhm.
Composition of analytic functions, addition, multiplication. That's really what we're dealing with.
Now you convinced me again. But so okay, so but then still this question of how do we define d hat? Because
Yeah,
d hat
Okay,
doesn't have any kind of analytic expression.
Yes,
well, yeah,
yeah, we should. But one time we should look at the limit of the actual, and the d hat is basically we call it in physical term an isorenormalization. In other words, d hat has to be necessarily different than d because of the non-linearity of the theory, etc., etc. And so therefore, as one solution is d hat is t multiplied by d. Now, but there can be others. There could be additional, however. This was the simplest possible, just to do some little physics. But there could be others, yes. No.
But
Incidentally,
it doesn't bother me too much if you had written simply d hat equals star d. Like I would say, oh, that's interesting because this
Oh, okay,
special
yeah.
operator really is pretty special. Right?
yeah, well, that's, well,
So you have to treat
Well, you-
d
you want it
as
to be
not
a,
as an operator or an element, but as like I mean not as a function and not as an element. It's an operator in the algebra, and it's not too much of a stretch to say, well, when we operate with hat on an operator, we mean star d, star operator.
yeah. Yeah,
Syntactically that makes good sense to me.
yeah, as you say, we
But
could, if we put the whole thing and put a star at the end of it, we could get rid of the I there. Well, Dr. Santilli always distinguishes between if the ISO unit is constant or not. That of course, when it's not constant, then you have to differentiate it as well. Of course, that means an extra term then. But the D operator, you see, forting is well defined because it's D of F, and then D goes through it, so that's two terms when I is a function of. So we want to keep the commutativity of the D operator as far as the product rule is concerned, Leibniz product rule.
I'm sorry I have to interrupt. Somebody was knocking at the door. To clarify the definition of I hat is equal to t multiplied by t, this is under the assumption that the variable is the ISO variable and not the ordinary variable. The reason being because if the t multiplied by t applies to the ordinary value, you don't recover the original dt, you recover t dt. So it's not an isotopy. So again, the necessity of lifting the ISO unit. Only if you have d hat of x hat, then you will end up t as a function of x, careful, t as a function of sx multiplied by t of x hat. Then this is indeed when it's equal to dx when I hat is constant. It's equal to dx. It's difficult to mm, it's difficult to do verbally. We should look at the equation.
Okay, well, I think we understand the issue. So I think
Intriguing,
Yeah.
very intriguing.
Yeah, I have nothing new here. That's really the end of it. Just trying to understand then the gradient operator. I wanted to find that also by sticking the I inside it. Well, anyway, so I agree that the problems seem to arise with the proper definitions of the derivation D and the integral. Maybe you can look at that some other time in more detail or something. Or see what Dr. Jeff will have to say about it.
yes, I think it would definitely be worthwhile asking Dr. Georgiev to maybe address this question more directly. And it's maybe he simply hasn't really got to that point in his series of lectures.
Yeah, keep in mind also that Dr. George does not necessarily define the iso differential on the iso function, on an iso field. And so the definition of the field is undefined in a number of these realizations. It doesn't need to. As a mathematician, doesn't it? We as a physicist, we got to do experiment. Numbers are part of a field. So our formulations are defined on a field. And for Dr. Georgiev, no. This is, I think, class of a series of realization.
Sí.
Okay, it's been very nice meeting the conversation. Yeah.
Okay, well, and I think we should encourage continued communication on this subject. And if there are some points that